Gravity and simple harmonic motion, review 11. Previously, we derived the maximum displacement x that this system can handle without the masses slipping is given by that expression. If we pull the spring farther than position x and release it, the masses will slide relative to each other. In such a case, determine the acceleration of each mass at the instant m2 is back at position x. We figured out how far we could pull back x and let it go without these two slipping. But if we pull it further than that and let it go, there is going to be some slipping. And the question here is, what's the acceleration of each of those masses at the instant that m2 is back at that x position, that initial position where if we had just brought it to there, the masses wouldn't slip. All right, so let's try this. Let's take m1 first. It's going to be sliding, so there's a kinetic friction force on it. Let's draw a free body diagram showing the three forces that are on m1, and then let's find its acceleration. m1, there's m1 right there, and it's going to have m1 times g down. It's going to have a normal force up. Let's call it Fn1, and that one is numerically equal, isn't it, to m1g. Those two are numerically equal. All right, when we pull this system back this way and let it go, the kinetic friction force is going to be acting in that direction on m1. And the kinetic friction force is equal to mu sub k times the normal force. So I'm going to substitute that in here to save a little bit of time. Just like that. Let's do Newton's second law. What's the net force on this? It's the friction force. Mu sub k times m1 times g. That's the net force. And that should equal the mass that we're talking about, which is m1, times its acceleration. m1 cancels. The acceleration of m1 will be mu sub k times g. So far, so good. Now, let's draw a free body diagram for m2 when it is at location x, at that very instant. And we're going to show all 5 forces that are acting. Let's see if we can do that. Here's m2 right there. We've got m2g acting on it. We've got m1g acting on that normal force on m2 from the surface, which exactly is going to cancel both of those. The normal force, I might call that Fn2, that is going to be numerically equal to m1 plus m2 multiplied by g. Then we have the spring pulling on this mass. And then what's the other thing? From mass 1, you see this friction force right here. It's pulling to the left on mass 1. Well, doesn't that mean that it's trying to hold back to the right on mass number 2? So this mu sub k m1g is going to be pointing in the other direction on mass 2, right here. Mu sub k m1g. Those are the 5 forces on m2. All right, let's write a Newton's second law equation. The ups and the downs cancel each other, so let's just do the equation in the horizontal direction. Kx is bigger than mu sub k m1g, so I'm going to make that positive. Kx minus mu sub k m1g, and that should equal the mass, which is m2, times the acceleration of m2. I'll put a little 2 there for acceleration. And it says to leave it unsimplified for now. Substitute the expression for x that was given in the problem statement, and there it is. So we're going to substitute this into that equation and solve that for a2. So let's see if we can do this without making a mistake. Actually, if we put that in there, the k's will cancel. So that means we're going to be left with mu sub s times g times the quantity m1 plus m2 minus mu sub k m1 g equals m2 times a2. I suppose we could distribute this out, and yeah, let's go ahead and distribute that out. All right, let's see if we can do that. A2 then is going to equal, let me distribute this out, mu sub s times g times m1 plus mu sub s times g times m2 minus mu sub k times m1 times g, all of that over m2. That's what A2 is. Do the masses have the same acceleration when m2 is at location x? What was A1? There it is. Mu sub k times g. That's what A1 was. There's A2 right there. We know what the coefficients of friction are. We know what the masses are. That's the acceleration. Do they have the same acceleration? No, they don't. They do not have the same acceleration, which means they are going to be sliding relative to each other.